pleasure to introduce Professor Spyros Kinnas, who is going to give the 42nd Weinblum Memorial Lecture. The Weinblum Memorial Lecture is named after Georg Weinblum, who was a professor in Germany, who many consider to be the father of modern ship hydrodynamics. He came to the United States for about 6 years after the Second World War and worked at what was then called the David Taylor Model Basin. Now we are called the Carderock Division of the Naval Surface Warfare Center. And when he passed away in the mid-1970s, the Society of Naval Architects and Marine Engineers here in the United States and the German Society of Naval Architects set up a fund to support an annual lecture in his name, which is given in Germany, typically in the fall, and then in the following year in the spring, except for the years when we're having the Symposium on Naval Hydrodynamics, in which case in the last 10, 12 years, we've been holding it here at the Symposium on Naval Hydrodynamics. And the first lecture was given in 1979 by John Weyhausen, who I hope all of you know. On to Professor Kinnas. He got his essentially bachelor's and master's degree combined from the National Technical University of Athens. Then he moved to MIT, where he got his PhD. He worked for about 15 years as a researcher at MIT, and then in 1995, went to University of Texas, Austin, where he is today. He's a professor of civil engineering who has specialized in propeller theory and propeller-related problems, which is what he worked on with Professor Kerwin at MIT. He has many graduate students who are well known. Two of his students are professors at the University of Michigan, and one of them, Julie Young, is attending this meeting, in fact, and she may be online listening to this. So anyway, with that, I turn it over to Professor Kinnas.
Thank you very much, Art. Let me share my screen. Can you all see my screen?
Yes.
I can.
Yes.
Can you also see my cursor?
I can.
Yes.
Okay, so let me just go to the beginning. Okay. Good morning, good afternoon, and good evening, everyone, all hydrodynamicists around the world. I'm very honored to give this lecture. I'm also very honored that I was selected to be the Weinblum lecturer of this year, and I thank the committee for this. Again, thank you for inviting me to give this lecture as well at the SNH. So I'm going to talk today about the latest work we have done in predicting performance and design of marine propulsors and turbines. I have here the list of students in the last 10 years, about 23 of them. And I definitely appreciate the support of all this work by ONR, as well as the consortium on cavitation we have at UT. So from propellers to propulsors, as you see here on the top left, we have a single all-type propeller, which started getting wider with skew, then started becoming more like sharp at the leading edge, surface piercing, contra-rotating, stator rotor, etc., ducted, tip loaded, and at the bottom end, at the right, I have a water jet, which is nothing else but another type of propulsor. So we try to model all these types of propulsors. Of course, there is a demand from bigger and faster ships, which means bigger, faster, more heavily loaded propellers. Cavitation is inevitable. Therefore, the design has to be balanced between cavitation and propulsor efficiency. So the computational methods that we have been developing, not only us, but everybody around the world, should be able to handle complex blade geometries, should be able to handle on and off design conditions, model all types of cavitation, be fast, because when coupled with design methods, trial and error systematic optimization methods, we have to have a fast tool to be able to turn in designs quickly. Should include interaction with hull or rudder or duct or hub or pod. And finally, the models should be able to predict propeller-induced hull pressure fluctuations as well as acoustic field far from the propeller. So there are many, of course, flow models we can use. And here I list them for a hydrofoil. We have at the top RANS models or LES models. The hydrofoil is somewhere here, and we have to have a large domain so that we have inflow and outflow conditions that are not affected by the body. We have, of course, boundary element methods where the boundary condition is satisfied on the surface of the foil. We have lifting surface, vortex lattice methods where the boundary condition is applied on the mean camber surface. And finally, we have single vortex where the hydrofoil is represented with a single vortex. And this is the equivalent of lifting line method for propellers and turbines. And of course, on the top, we have a method which is definitely slower and difficult, of course, to grid the space, as opposed to having faster methods at the bottom, which are, in addition to be faster, also are easier to model, or if you like, to discretize the surface as opposed to the volume. So going down, I have here propellers on the top left, modeled with a vortex lattice grid, and we solve actually for the bound vortex of those bounders that you see. Boundary element method, where we panel the blade, and we solve for the perturbation potentials, which are equal to the dipole strengths on the panels. And at the bottom, I have, of course, RANS, which solves for all these primitive parameters, velocities and pressure. And in this case, you see a propeller being down here in red, and you see the grid around it, which again has to extend to quite some distance in all directions so that we model the flow so that the far stream conditions are not affected by the propeller. And of course, this is showing only one blade by using periodic boundary conditions. Now, the advantages and disadvantages of the methods, of course, the surface methods are inviscid, and the effects of viscosity need to be accounted for either by semi-empirical adjustment of the pitch and application of viscous coefficient, or via coupling with integral boundary layer surface. In addition, vortex lattice methods do not include the effect of thickness. Therefore, a thickness loading coupling needs to be applied to make them closer to boundary element method. Of course, the finite volume or RANS and LES methods include the effects of viscosity inherently, but you have to be sure that you have enough resolution within the boundary layers that are developing due to the effects of viscosity. Of course, surface methods, panel methods, or vortex lattice methods, they need to approximate or determine the surface, the trailing wake surface, the surface of the wake, of the trailing wake, by using a wake alignment model. And finally, of course, RANS and LES do not need to model this trailing wake surface, but in order to get it right, you have to make sure that you have enough resolution downstream of the propeller in the wake of the propeller. And that not only helps determining where the right surface of the wake is, but also it helps with reducing diffusion, numerical diffusion. So going down the list, in the boundary element methods that I primarily am going to present here, to solve the flow and evaluate the performance of propeller, we need to know what the inflow is. Often the propeller inflow is measured or evaluated via CFD or via runs. Needs to be known behind the hull at the propeller plane in the absence of the propeller, and this is what we call nominal wake. However, due to the hull-propeller interaction, in the end, we need to evaluate the so-called effective wake. So for a simplistic, if you like, understanding of why we have to evaluate the effective wake, assume that we have a non-uniform inflow coming with a vorticity in it coming into the propeller blade. As you, I think, is easy to see, at point A of the propeller, the inflow would not be the one just upstream at point C. Due to contraction, it would be the flow somewhere above point C at point B. Therefore, the propeller wake is going to be different from the nominal wake. Again, this is a simplistic view. And here comes a general definition of the effective wake. Effective wake on the left is equal to the total wake, total inflow, including the effects of propeller inflow, everything, minus the propeller induced. So this is how we are going to evaluate the effective wake. So going down the list here, first of all, before I show you any details, I want you to see the importance of having the effective wake. Here we have this propeller, I think it is 5168. And here we have a nominal wake shown on the left like this. And on the right, I show the effective wake after an evaluation of that, as I show you in the next slide. So the KT and KQ is first of all predicted by using full-blown runs, then by using BM with a nominal wake. And you see that using a nominal wake, the KT is going to be 13% in error, and the KQ 11% in error. And by using now the effective wake, the correct, if you like, effective wake, then we're going to have a much smaller error, again, compared in this case versus runs in less than 1%. So how do we evaluate the effective wake? As I said, this is the general formula we use. And this is a flow chart that shows how this is done. We start, of course, with initial guess of the effective wake field. And then based on that, the BM or the vortex lattice method are going to give me the propeller perturbation flow, as well as the mass source and body force. With this body force, runs with sources which are equal to those body forces, runs is running, and this gives us the total velocity. And then by subtracting the effective wake, the propeller induced velocity from the total velocity, we get the effective wake. And of course, we go around that until convergence. So one thing I should say, I already mentioned that, in order to evaluate the effect of the propeller within runs properly, the propeller pressure forces need to be converted into body forces, and the propeller thickness needs to be converted into mass sources. And also I should say that in all this approach, we use time averaged forces and sources to, if you like, expedite the simulation. So going down, another thing that is important is where you are evaluating the effective wake. Traditionally, we have been evaluating somewhere upstream of the propeller blade, but most recently, we have decided that the best is to evaluate the effective wake at the propeller control points, as shown here. This is a case of a ducted propeller where the duct is handled and the hub are handled by using runs, and the propeller is handled by using a boundary element method. You see here where the propeller is, and here you see how the propeller is modeled with body forces within runs. what I show on the top right, at the bottom right, is the performance from experiment. And as predicted, if we use the control, if we evaluate the effective wake somewhere upstream of the blade versus at the control point. So you see, if we use it upstream of the blade, definitely we miss a lot, as opposed to evaluate it at the control points where the simulation is much more successful. So that is one lesson to learn from this. We have applied that in the case of podded propellers. As you see here, two podded propellers, front and back, and you see here the body forces, the mass sources, the axial body force, the circumferential body force. And I wanted you to see here at the bottom where we show the swirl velocity. And it's a little bit hard to see, but I tell you that the swirl downstream of both propulsors is quite minimal, meaning that this is a good design, because downstream you have to have the smallest swirl so that you have the best efficiency out of this podded propulsor. And here it shows the KT and KQ as compared with experiments. So then we applied this in the case of a propeller working with a hull and a rudder, as you see here. And of course we did, this is for we are going to make comparisons of this with an experiment performed at SSPA, where they put this model inside the SSPA tunnel, cavitation tunnel. And here I want you to see the axial force and the circumferential body force as predicted from the method. And also here you see the nominal wake and the effective wake. Again, I want you to see how different the two are from each other. And finally, the KT and KQ of the propeller are compared with those measured at the SSPA tunnel. So going down the list, one thing I wanted to tell you is that we also have a time accurate modeling of this interaction as opposed to being time averaged. And in that case, the time accurate forces are changing within runs. As you see here, the body forces are definitely moving around with the propeller. And here, this is in the case of a hull in maneuvering. And here we show the flow, the vorticity, in fact, around the rudder and the propeller, behind the propeller, from full-blown runs at the top, and under from BM representing the propeller coupled with unsteady runs. So I think the simulation seems to be, our simulation seems to be very well reproducing what would happen with the full-blown runs, where runs applies, a steady runs actually applies both to the propeller and the hull. So going down this, as I was saying earlier, the trailing wake surface is something that needs to be evaluated. Of course, the trailing wake surface has zero thickness. Since it is massless, it has to be force-free. And in the axisymmetric flow, we have to make sure that the mean velocity vector and the surface of the wake are tangential to each other. Oops, sorry, I went too fast. Tangential to each other. And in the case of axisymmetric flow, again, the two have the propeller, the velocity induced in the wake and the surface have to be tangential to each other. In non-axisymmetric flow, of course, we require the vorticity to convect with the local flow. And we have done both of these, and I want to show you how important, first of all, is to have the right wake. This is shown for a propeller. I think this is 43, 48, if I remember correctly. And this shows the performance, KT actually, thrust coefficient versus advance ratio, predicted from experiment with the crosses, from runs in yellow, and from using full wake alignment, which is shown here, versus using approximate wake alignment by using an older method. And you see definitely you have to have the right location of the wake to get the performance right, as opposed to having an approximate model. So again, this is something that actually we show even more pronounced in the case of ducted propellers, where if we align it by using the propeller wake, by using all the, if you like, technologies, the experiment is down here and actually runs, and also by using the full wake alignment. And here, if we use the simplistic alignment models, and for the KT and KQ, so as you see, we miss a lot by not using full wake alignment. So it is very important in the case of ducted propellers in particular. And in fact, we push this model even further, where not only we aligned the wake of the blade, but also the wake of the duct. So I want you to see here, I hope you can see the dark lines here, show how the wake alignment scheme from our method is able to predict the roll-up of the vortices. And as you see, it matches very well the location of the vorticity shown in color as predicted from runs. And of course, the performance here from all these models, KT of the duct, KD of the propeller, and KQ of the propeller are all predicted, I think, very well with all these models. So again, this is something that is important to emphasize one more time, that having the right effective, right location of the wake, trailing wake is an important aspect in all these models. And we did that in the case of a propeller in inclined flow, 10 degrees in this case. You see, I wanted to see here in black, it shows the vorticity as the wake location as predicted from our method versus the vorticity plot coming from runs. This shows again the flow, and on the right, it shows the KT predicted from runs, and from BEM, the KT now is going to be unsteady because we have non-uniform flow. And I want you to see how well runs and BEM agree with each other. And of course, finally, they agree also with experiments where we look at the amplitude of the first harmonic of the axial force. So we're very happy to see this. And finally, it is important to include the effects of boundary layer as well. And we have done that by coupling the method with X-foil, but with a modified X-foil, where X-foil, of course, is a two-dimensional method. The way we have applied it, we took all the influence coefficients of X-foil, let's say at a blade section, and we replaced them with the three-dimensional influence coefficients. In other words, three-dimensional sources and dipoles. But this is not enough. We also had to take into consideration the effects of the other sections on the blade, as well as other sections on other blades. And all of that, of course, helped us in having better, if you like, correlations. Here I have the top figure on the right is a little bit hard to see, but essentially what this tells you is runs using full wake alignment with boundary layer, full wake alignment only, and simplified wake alignment with boundary layer, all these approaches. In the end, as you see down here towards the trailing edge, this is a blow up of this. It is, you can see from here that the most successful of all is when we have boundary wake, full wake alignment and boundary layer corrections together. So again, all of these things show that having the wake right and having the effects of boundary layer by using this, if you like, sort of three-dimensional scheme where you take into effect the boundary layer sources on other sections and on other blades is the best approach. And here I show you for one more time, two other propellers, 4381. Experiment is shown in red, and here shows full wake alignment plus boundary layer in blue, and all simplified wake alignment with boundary layer, and obviously full wake alignment with boundary layer is more successful. And here also is shown for propeller 5168, where you see in the experiment is with red dots, and boundary element method with no boundary layer is shown in dark line, and in a red line, boundary layer method with boundary layer corrections, and obviously this is the most successful of all. Then I'd like to go quickly into a new extension we have made in our panel method in order to be able to handle not only sections with sharp trailing edge, which is often the exception than the rule, but also sections with sharp, non-zero thickness trailing edge, round trailing edges like that, or trailing edges like that that are used for anti-singing. So how do we do that? Well, again, let me show you first how this model works in 2 dimensions. We take, let's say, this propeller with the round trailing edge, and we extend it with these red lines up to a point C. The location of point C, in other words, the X location, the Y location, are to be determined. Also, the location of point A and B are to be determined from the scheme. In between A and C, we have a second order curve which has a proper continuity at A, and the same for the bottom curve. So in the end, the unknowns that we have here is the location of point C and location of point A and B. How do we determine those points? Well, in fact, through a Newton-Raphson scheme, Newton's second, I should say, scheme, we are able to impose the following conditions. First of all, we want the lift of this extension to be 0. Also, we want the moment of this extension to be 0, which is one way of saying that the pressure distribution over this extension is going to be constant, something that has been verified by runs and I think also in experiments. Then point A and B are determined via coupling with X-foil, boundary layer code, where we make sure that the CF at point A and point B is equal to 0. So in other words, where we have separation, where CF is equal to 0. So all of these conditions have been implemented, and there it shows, actually this is for a bare duct case. It's a ducted case, not a hydrofoil, but without the propellers. Here it shows the flow from runs. Here it shows the model, including our extension. And here it shows the pressure distribution at the top for Reynolds number 10 to the 6 and bottom 10 to the 7. And you see the correlation is very good as produced the pressure distribution from our method and from runs. So we were very happy to see this. Then we extended this in the case of propellers by using a similar scheme, of course, much more complex. This propeller was provided to us by one of the consortium members. We gave it a name, blunt trailing edge, or blunty, if you like. We are not allowed to show you what the geometry is, but actually you can see somehow the geometry here. And I want you to see that all of these sections have a round trailing edge, which has been extended. Here you see it in a local coordinate system, and here you see it on the propeller. And of course, the extension works the same way. Now we have to determine the location of point C, XC, and YC at every section, okay? And here it shows, again, we have to have a similar scheme, but now more sophisticated. And here it shows the initial, XC, the final, in orange. Also for YC, which is more, if you like, sensitive, it shows the initial and the final. And now how do we do it? How we determine the location of these points? Again, by using the same approach, where now we require at all blade sections, the local force, the local lift at every blade section of the extension, the local force of the extension and the moment of the extension to be equal to 0. And in fact, this shows the delta F, as we call it, the force on the extension, by using in this color, in red, is by using a initial guess, by using an arbitrary extension here in orange, the same for the moment. You see, when you use arbitrary or initial guess, you don't get it right, but later on, by using actually more sophisticated Newton-Raphson or optimization schemes, we are able to get delta F and delta M very close to 0. And you see how this affects the circulation over the blade. All of these methods produce essentially identical circulation. All of these methods for solving this multidimensional system of equations of having delta F and delta M equal to 0 everywhere along the span of the blade. And here it shows if we use the initial guess or arbitrary extension, we get much different circulation. Of course, how does this compare with experiment? This is the next thing I want to show you. And we have done, what we have done here, we have also used runs, star CCM plus in this case, in order to model the flow around this blade. And again, I should tell you, we have to be very careful with this blade. These blades or blade sections with round trailing edge are difficult to model in any type of model we use, any type of method we use, even within runs. Because as I told you earlier, you have to make sure that the trailing wake is modeled properly. And in this case, since we use an O type of scheme, it's very hard to have a trailing wake which is modeled sufficiently at a sufficient distance from the trailing edge. So again, with using star CCM plus in our method, we have here the KT from experiment in a solid line. The current method with using this extension scheme is a little bit above. RANS is a little bit below, and the same with the KQ. And here it shows the pressure distributions from RANS and from our method. Again, they are not on top of each other, but they are close enough. And I think more work needs to be done in that respect to make sure that we get closer to the experiment, I would say, from both methods. So then I'd like to go further into how we model the effects of cavitation. We model, of course, cavities with elements, boundary with panel methods, with panels, and we require the vapor pressure on the cavity to be, the pressure of the cavity to be equal to vapor pressure. And of course, the method is able to determine unsteady cavity patterns, fully unsteady, not quasi-steady. And the method allows for mid-chord cavity detachment, as well cavities on either or both sides of the blade. It also allows for modeling, if you can see here, it's so more clear here, of the developed tip vortex cavity, so that we are able to predict developed tip vortex and the pulsations of that vortex. So this shows comparisons with an experiment that was performed at MIT long ago. You see the tip vortex here, and here you see it in the experiment, the developed tip vortex and the cavities on the blade. So this shows the simulations at the bottom and the experiment at the top. And here I want to show you this movie that shows the developed tip vortex. And it's a little bit hard to see, but this vortex, in fact, the developed tip vortex is changing its shape as it is adjusted to the inflow. So that is actually an important characteristic which has helped us evaluating the effects of developed tip vortex and its pulsation on the hull pressures. So let me continue from this. We have applied this on tip-loaded propellers. And I wanted to see here, we have two vortices coming from the knuckle of the tip-loaded, of the winglet, I would say, and from the tip of the winglet like that. And here I have again some movies that show you the predicted cavitation at a higher cavitation number on the left and the lower cavitation number on the right. Let me continue with this. Oops. This shows prediction of the pressures on the hull, and I wanted to see that how well the wake of the propeller is modeled on this. So I'm going down here. This is now for a plate, propellers on, propeller-induced pressures on a plate. And you see the tip-loaded propeller, in this case, under it. That is an experiment that was performed some years back. And In the next slide, I want you to see at all these points on the plate, this point in green is the point just above the propeller, and these points are, these are towards the stern, and this is towards the bow. And in the next slide, I'm going to show you predictions versus measurements of the induced pressures on the hull. And in red, you see runs. In black, you see BEM. And the experiment is shown with circles. And I think I find this a successful, if you like, correlation both for BEM and for runs. So then we were very happy to see this. Again, this shown for all the points. Now I would like to go very quickly through how we have used that in optimizing a propeller. In other words, design via optimization. This is something we have carried out long ago. And our approach here, instead of using systematic series like Wageningen or other type of series to design propellers, or more sophisticated methods that they use lifting line method in order to design the propeller blade loading and then design the blade geometry to adjust to that loading. Instead of doing that, we use a different approach, which is actually design the propeller in the actual inflow, where the circumferential variance of the inflow and the effect of cavitation are considered within the design process, not after the design process. There is no need for trial and error, okay? And we can put, of course, constraints on cavity extent, volume, and its effect on the hull pressure fluctuations. And our approach can design either fully wetted propellers at low loadings or cavitating propellers, and show you examples in just a moment. How do we do that? Well, we model the propeller with a B-spline polygon, as shown here, most of the times 4x4 B-spline polygon, and the location of the vertices of that polygon, usually we have 13 or 16 variables, are the variables that we need to determine in order to determine the shape of the blade, okay? And that means the pitch as well as the camber, okay? Not the thickness is given. So how do we do that? Well, we have developed as it's shown here at the bottom, a constrained nonlinear optimization based on augmented Lagrangian penalty method, something that we have developed more than 25 years ago, where we minimize the torque for given a thrust, KT, with given, if you like, maximum cavity area, in the case of cavitating propeller, or in the case of fully wetted propeller, requiring to have the minimum pressure being a little bit below the cavitation number so that it doesn't cavitate. Again, this constraint is given like this, an inequality constraint. And most recently, actually, we imposed another inequality constraint that requires the pressure at the bottom of the blade to be greater than the pressure at the top of the blade. And this actually allows us to avoids negative loading and the presence of phase cavitation, which quite often can be bad, detrimental, if you like, in terms of erosion. I'd like to show you a couple of examples here. In the case of an inflow shown like that, with a KT, which is 0.35, with J, which is equal to 1. And in this case, I should say the model that we use is a vortex lattice method, MPA3A, the method that we have. And one thing I went very quickly over here, I should say X here is nothing else but this 13 or 16 variable vector that we need to determine. Now, how do we determine KQ and KT? Well, by using MPA3A, running it consecutively and interpolating from previous MPA3A runs the KT and KQ. So again, by using a linear interpolation in the beginning and then second order Taylor interpolation, if you like, so that we have a better, if you like, interpolation within previous MPA3A results. We can do that also with the panel method, but only I'm going to show you results by using MPA3A within this model, which we call CAVOP 3D. So the inflow is non-axisymmetric in this case. And from this run, we require the cavity area to be less than 30% of the surface of the blade. And we required and we got, as I will show you in a moment, a blade with a cavitation in it. The eta that came out of it is 72.50 to 72.5%. So now I'm going to show you the cavity patterns, and the maximum is again about 30% of the blade. Again, of course, it changes as we rotate around. And here I want you to see the convergence history. I want you to see that KT and KQ in the beginning, they vary very violently. And this is good. We like that because we would like our design method to go through a variety of possible solutions. So it is good, but eventually it converges into a solution that does not change with number of iterations. And I should tell you how important to have a fast tool in this case, because with about 600 MPA3A runs, it took about 1.5 hours with one CPU. So that was very, I think, good to see. And then what we did, we required a constraint of 60%. We allow more cavitation. In this case, we get an eta, which is a little bit higher as expected. The more cavitation we allow, the more efficient the blade is going to be. And this is something we knew from the past, but now we see it quantitatively with the tools that we have. And this, of course, has more cavitation as expected. And this is the, if you like, the convergence history for this second run. Finally, I'm very close to the end here. I would like to tell you that we have started looking into designing now a propeller, in this case for an axisymmetric body, so that the propeller is able to push, of course, that body at a certain speed. Now, the situation that we have here is we don't know the inflow to the propeller. And also, we don't know what the thrust of the propeller is. So what we need to do is we need to start with a given inflow, which can be, in this case, the inflow that corresponds to the speed that this body needs to go with. Then, based on that we design the propeller to have, if you like, the best efficiency by using CavOp3D. But then once we design it, we need to put it back into our model, where now we use runs coupled with MPA3A in order to find the interaction of the hull with the propeller. And that interaction not only is going to provide me the correct inflow to the propeller, but also is going to give me the correct resistance of the hull. So I want you to see here, when we start, the propeller thrust over here, the design that for which, what comes out of the design has a KT which is too low. The resistance in this case is too high, and eventually the two converge until in the end we have the thrust equal to the resistance. And of course, in this process, we have determined the correct inflow, the effective wake, this shows the effective wake to the propeller, and the design which, as you see here, we have a very favorable pressure distribution where you don't see any peaks at the leading edge. So this is, if you like, the correct pressure distribution, which has more or less flat pressures on both ends. And I would like here to show you the convergence history. Again, as I told in the beginning, we have very big excursions, but in the end, we have convergence. And here, I'd like to show you a movie that shows how the blade design with the iteration converges to the right one. And you will see towards the end of the movie, you will see the blade not moving anymore because it has converged. Let me play it one more time. You see playing in the beginning, until finally it converges to the correct, if you like, design. So again, we were very happy to see this. Again, this is progress, I think, that makes us happy. Of course, there are always issues that we try to fix with our methods, and we keep making progress. So let me now tell you very quickly about turbines, which is nothing else for us, nothing else but another blade, if you like. You see here different type of turbines, counter-rotating turbines here. CGen over here, and one that we have designed. A propeller is the same thing as a turbine. There is some difference in terminology. In propellers, we use the advance ratio. In turbines, we use the tip speed ratio. And the two are related through this magic relationship. TSR times J is equal to pi. This shows the triangle, if you like, the velocity triangle for a turbine, and this shows it for a propeller. Not a lot of difference in terms of hydrodynamics, if you like. This shows how successful a lifting line method can be in predicting the circulation distribution around the blade by using a lifting surface method with different number of elements, and this is using lifting line model. And of course, for a turbine blade, which is very skinny, you expect a lifting line method to be very successful, and this is shown through this, if you like, graph. So going down, this shows a prediction of the power coefficient by using different models, including also Fluent in this case, as well as our model, lifting surface, and vortex lattice method. PropCav is our panel method. And you see they're, I think, more or less successful in predicting the performance. We have more of this shown in more recent publications. Here shows the prediction of cavitation on the blade, and here as we predicted. And one thing I should tell you here, wake alignment is even more important for turbines. Why that? Because the turbines usually work at very low pitch. And as you see here, you have to have a lot of turns of the wake and a very big length of the wake in order to predict the correct effect of the wake on the blade. So it's even more important than for the propellers. And this is shown actually in the next slide, where we have applied this full wake alignment model on a lifting line model that we have developed. And you see here the Batch's limit that we all know is 0.559 something. And here it is what we get from applying this lifting line model, where we use a traditional lifting line trailing wake model, as opposed to applying a full wake alignment. And I wanted to see that now, to the limit of high TSR, we approach the Batch limit, something that we were not able to do. And that was a big mystery, not only for us, but for other people that work on turbines. So wake alignment is even more important for turbines. So finally, I wanted to show you some exercise we did at UT. Actually, this was a project that was conducted by my students in my undergraduate senior level class of ocean engineering, where we had, by using the lifting line model, design the duct as well as the propeller blades. And we tested, and I should really mean tested, because actually we designed it, all these ducts that we came up from our design method, different ducts, different blades as you see here, all of these were printed at the three-dimensional printers we have at UT, and the students tested them. And I wanted you to see in the next slide. Here we show the power coefficient for different duct lengths. And in this particular case, you see the bigger the length of the duct is, the bigger the power. Also from the angle of attack. And I want you to remember something here. The angle of attack is defined as positive in what we call the opposite direction. And you see, it has to be a diverging duct. And I wanted to see in the end, by actually doing all these experiments with duct, we found voltage that came out of this, because we have connected this to a, if you like, to a motor. The voltage with duct came higher than that without the duct. And one thing I wanted to see here, let me only show you this. This shows the the experiment that we did. And you see in the flume as the propeller, okay? And then Very quickly, and this is going to be the end, we have also made a big effort to develop a new method that takes in consideration the effects of viscosity. We call this VISVI, and we do that by using the vorticity equation, which actually is capable, this is my last slide, which is capable of, instead of having the propeller in a traditional runs method being using, if you like, a larger number of elements, 1.5 million cells, by solving the vorticity equation only around the blade, we're able to do it with much fewer cells. You can see more about that in the presentation of Thursday morning by my graduate student, Mr. Wu. And this is the end. What we would like our group to do more, we would like to model the developed tip vortex cavitation and its effect on the hull pressures. In fact, we have done that, and we got some very encouraging results where we are able to predict higher harmonics better now, and this is shown in this presentation. We'd like to evaluate the acoustic field, and we have started doing that by using Fox-Williams-Hawkins equation. We'd like to apply VISVI, this new method we have been developing in the case of turbulent propellant flows and cavitating flows. We have already done this in 2 dimensions. And finally, we'd like to test further CAVOP with the effects of hull and apply to design of propellers for ships, ducted propellers, and counter-rotating propellers. So all of these are the future challenges we'd like to attack. Thank you for your opportunity to present our work. Looking forward to your questions. If there's no sufficient time, please send me your questions to this email address. Thank you again for your attention.
Thank you, Spyros. We're really at our time limit, so we're not going to have time for questions. There have been some questions submitted. I will see that those questions are captured and get to Spyros. I had a question for him also. We will see that these questions are answered and distributed, although I'm not quite sure what that route is. Anyway, thank you again, Spyros. And
thank you.